Okay, welcome back. So today we'll do the Chapter 3 portion of the text, and this will regard trigonometric functions of angles. So, all right, so we're going to start off with a sequence of definitions. And we have the following results, fundamental results. So we're going to be talking about angles, and as kind of alluded to in the lecture for Chapter 2, we have components of an angle. So here in the first illustration, I exhibit an angle which is defined as follows. It's essentially the formed by the intersection of two rays in the XY plane. And the intersection, we call it point O, which could conceivably be the origin of a circle. And we have the initial side, which is ray OR1. And then we have what's considered a terminal side, right here, a terminal side, which is ray OR2. So these are the two pieces of what constitute an angle, an initial side and a terminal side. And a positive angle is formed by taking ray OR2, this ray right here, and rotating it counterclockwise from the initial side. So when you rotate in this direction, counterclockwise, we say that this is a positive angle. So if we look at the negative angle exhibit, if we were to rotate ray OR2 clockwise from ray OR1 in this direction, clockwise in this direction, then the resulting measure will be a negative angle. All right, so in this case, in this illustration, it's kind of hard to see this circle that I've drawn. So let me kind of work on making it clearer. So here we have a circle, and I'll do the best I can. So there are a couple more formulas to understand before we proceed to some applications. Okay, so here's the circle. Okay, and so I'll call it a unit circle in the XY plane centered at the origin. And so we have the vertex. So this point right here is called the vertex of, say, this particular angle. So we have this angle. Oops, sorry, got my trace got messed up. Okay, so we have the confluence of these two rays that form an angle is called a vertex. Okay, so we'll call this point right here the confluence, the vertex. Okay, and the vertex of this particular angle that I've accentuated in blue is at the center of a circle. And we measure this angle theta. This is a Greek letter uppercase theta right here. Okay, is measured in radians. Okay, so the length of the arc that subtends an angle of 180 degrees, as we discussed last class or last lecture. Okay, so this arc length that subtends an angle of 180 degrees is called pi radians, and that's a definition. Okay, there's no proof involved in that. It's just defined that way for the unit circle. Okay, so this is an important relationship to memorize. Okay, so we talk about arc length. So for instance, if I wanted to find the length of this arc that I'm accentuating in black, okay, we say that S is the arc length, and it's measured as the radius. In this case, the radius is 1 times the measure of the subtending angle in radians. So for instance, if this were a unit circle and theta were pi 6 radians, or 30 degrees, then the arc length would be pi 6 radians. Okay, or if in the case if the unit circle were measured in inches, then the arc length would be pi 6 inches. Okay, so if you know the unit, you can replace radians with that particular unit, whether it's inches, centimeters, meters, and so forth. All right, and then we talk about the area of a sector. So let's see here if I can. What's a good color? Cyan, maybe? Okay. So Where's my, do I have a brush? No, that's a fill. I don't know if I have a brush. Let's see if I have a brush. Yeah, paintbrush. Okay. So let me choose, say maybe, what's a good color? Orange, maybe? So this sector that I'm filling in, brushing in with orange, okay? We can calculate its area in square units, okay? The area is defined as this formula right here. It's 1/2 times the radius squared times the measure of the subtending angle in radians. So we have this for the consideration for the area of a sector. Okay, so this is called a sector. The area that's shaded in orange is called a sector of a circle. All right. So let's see here. So let me pull up another technical note, next page, and I'll extract something from the notes. One second. I'm pulling something from the notes here. Just a little pause here in the display. All right, so some more terminology for you that I'll wire up here in this whiteboard. So we talk about an angle being in standard position. And the way we consider an angle being in standard position, if it's drawn in the XY plane as shown in this illustration, with the vertex at the origin. Okay, so for instance, consider this angle right here. Right there. Oops, that's not drawn very well, is it? I need to be careful. More careful. So let's see here. So here's the terminal side. Vertex at the origin. Here's the initial side. Okay, so there's my angle. And so it's in standard position with the vertex being at the origin. The initial side right here, it's on the positive x-axis, which it is. All right. Okay, so this angle in blue is in standard position. And two angles in standard position are coterminals if their sides coincide. Right. So for instance, we have the blue angle, and then we can, if we say, suppose we decide to draw another angle of, say, we start here and we take one lap around, say a circle in some sort of circular motion. So that where I'm stopped right now is 360 degrees, but suppose I go this axis right here and I form this angle shown in red. Okay. Well, that angle originated by going 360 degrees plus whatever this distance is. Say this is another 30 degrees right here. So suppose the blue angle is 30 degrees and the red angle is 390 degrees. Okay. So if, all right, so we have the measure of angle A is equal to, say, 30 degrees, as shown in the illustration, just supposing. And then the measure of angle B, the red angle, is equal to 390 degrees. Well, you notice that both of the angles are in standard position, and the initial side of both angles are the same, and the terminal sides of both angles are the same. So these two angles are considered coterminal because their terminal sides line up, and following with the caveat that they're in standard position, so coterminal. Okay. Coterminal angles. All right. So let's see here. Oh, and then, okay, so now we can talk about some other parameters, namely from physics. Okay. So suppose a point moves along a circle. Of radius r, and the ray from the center of the circle, array from the center of the circle to the point traverses theta radians, okay, in time t. All right, so let's see here. Let me pull up the math tool. So we're going to let S equal to R theta. So, okay, so that's the position. Okay, so let S equals R theta. So what is S? So S is equal to the distance the point travels in time t. Okay. So let's see here. Can I draw a figure? Shapes here. There's some shapes. Okay, so here's a circle. And let's see here. Suppose, what do? Let's give it an XY plane for reference, okay? So let me annotate the XY axis. Okay, so here's my XY axis. Oops, Control Z. Let me move my circle away. So let's move it here for better drawings. Okay, and so let me superimpose a coordinate frame on the circle. So here's my x-axis. Here's my y-axis. And then the radius of the circle is r. Not necessarily the unit circle, but the radius is r. Okay, and so the motion of S. So suppose S starts at this point, and then it goes counterclockwise along the perimeter of the circle of radius r, and say it stops right here. Okay, so the distance it traverses is this. S is equal to r theta. So we know r, and then theta will be this angle right here, the measure of this angle in radians. So here's your theta. Okay, so S is equal to r theta. So here's your S. So this distance right here is S. Okay, and so S is equal to r theta. Okay, so now, so that's distance. Now we have what's called angular speed. Okay, so angular speed is the change in the measure of the angle of the particle with respect to the origin. So I'll write this down. Angular speed, the change in the measure of the angle theta with respect to t. Okay, so so that angular speed is how fast. The particle, of course, is in motion. The particle is in motion around this circle, and so we want to know how fast theta is changing. Okay, and so there's a formula for that. We'll write it as follows. So we have, let's see, math equations. We have omega is the Greek letter omega is the quantity that denotes angular speed. And so that is equal to theta over t. Okay, so this is angular speed. Change in theta with respect to time as the particle or the point moves around the circle. Okay. Now, angular speed. So now the other quantity that we'll have is called linear speed. So we need to compare that with linear speed. So linear speed is the velocity of the point. Okay? And so linear speed is equal to the arc length, the distance it's traveled divided by time. So we'll write the formula for that. So F is equal to, V is equal to, that's your linear speed. And let's see, we all have a rational function here. That would be F, your distance traveled on the circle, divided by the time it takes. So that's your linear speed. All right, so motion along the unit circle. Okay, linear speed right there. And then angular speed right here. So we'll have some problems where we have to calculate both of these quantities. Okay, so let's see here. Can we do some problems? Let me see, from the book. Or an older book at least. Let's see. It's chapter 3. You may not have this, but I'll go ahead and work it. I'm looking in the book now for some example problems that I can work. Thumbing through the text here. Okay, so like in this question, let's do some examples. So let's find an angle between 0 and 2 pi radians that is coterminal with the following angles. Okay, coterminal. All right, so in this case, so suppose, let's see, I have negative 7 pi over 3. So let's do that. So let me write. We want to find an angle between 0 and 2 pi. It's coterminal with negative 7 pi over 3. All right, so let's see how we can investigate that. So let's see here. If I go back to my shapes and let's pull it out. Oops, Control Z. Let me draw it big here. Okay, so here's a circle, and we'll overlay a coordinate system. Okay, so 7 pi over 3. So where is 7 pi over 3? So we know negative 7 pi over 3 is equal to what? Negative 2 and 1/3 pi. Okay, which is equal to negative 2 pi minus 1/3 pi. Okay, and so if we were to start at the point 1, 0, okay, and we go negative 2 pi, we'll go in this direction, right? So here's negative 2 pi. Okay, so here's negative 2 pi. And then we go another pi thirds in the clockwise direction. Okay, so we go another pi thirds. So right here, we'll say is negative pi thirds. Okay. So when we when we take a lap, -7 pi-thirds radians around the circle, we'll end up somewhere here in quadrant 4. So but the problem says we need to find an angle between 0 and 2 pi. All right, so that's coterminal. So the angle -7 pi-thirds happens to be right here. Okay, and so what is an angle between 0 and 2 pi that's coterminal? Well, to do that, we have to go counterclockwise, right? Because between 0 and 2 pi, we need a positive angular measure. So in going counterclockwise, we go to pi halves, okay? Then here's pi, okay? And then here's 3 pi over 2 right here. Okay, so we come to 3 pi over 2. Sorry, 3 pi over 2. And then we have to traverse this distance right here. So, so what is the remaining distance right here? And then we'll add this distance that I've just shown with the right here to 3 pi over 2. But there's an easier way. We know that the reference number for negative pi over 3. Okay, so if t is equal to, if the terminal number is negative pi over 3, then the reference number for t is pi-thirds. Okay, and so a positive angle that's coterminal with -7 pi over 3 would just basically be 2 pi minus the reference number, which is equal to 5 pi over 3. That's one way of looking at it. Or we could say, okay, we could add to 3 pi over 2 right here, this residual distance, and so this would be what? If this is negative pi over 3, so that would be a little more challenging to calculate. So it would be basically 2 pi. Yeah, it would basically be this formula again. It would all come back down to this formula. So continuing our journey, this blue angle that I've just accentuated now is coterminal with -7 pi over 3. Okay, so you just basically take 2 pi, subtract off the reference number, and you'll have the angle that's coterminal. All right. Let's see, how about number 38? So in 38 we have 10 degrees, or 10, not 10 degrees, but 10 radians. So we want to find an angle between 0 and 2 pi that's coterminal with 10. So what angle is coterminal with 10? Okay, so where is 10? So 10 is, well, here's 2 pi. 4 pi is greater than 10, right? So 10 would be, perhaps, let's see, so we can divide 10 by pi. So I'll need my calculator. Pull up the calculator and divide 10 by pi, and I'll show you why, explain to you why I'm dividing 10 by pi. So 10 divided by pi is, where's pi? 3.18. Okay, so approximately 3.18. So 10 is equal to 3.18 pi. So that means, where's 3 pi? So 3 pi is here. So 3.18 pi is probably here. So this would be 3.18 pi. All right, so we would want to find an angle between 0 and 2 pi that's coterminal with this angle. Okay, well what if we took 10 pi, which is here, okay, and subtracted off 2 pi. So 2 pi is, so what if we considered 10 minus 2 pi? Now, why did I use 2 pi? Because 2 pi, if I stay here and if I subtract off 2 pi, then that means I go clockwise one time around, okay, from this point. So go clockwise one time around and I'll be coterminal with it. And it happens that 10 minus 2 pi is 3.18 pi minus 2 pi, which is equal to 1.18 pi. And of course 1.18 pi is between 0 and 2 pi, right? So all I have to do then is note that it just so happens that 10 minus 2 pi is 1.18 pi, so I know I'm in the range, and I know it's coterminal. This angle is coterminal because I just started at 10. I started at 10, and then I just took one lap around clockwise, 2 pi, and I came back to the same point. So I came back to the same coterminal angle. Okay, and that is 1.18 pi. So 10 and 10 minus 2 pi are coterminal. Now this may not always be the case. You could have other situations. All right, so let's see what else we can work. All right, so how about, so I have a word problem. It's kind of interesting. Let me paste it in the whiteboard, so bear with me while I cut and paste here. And I think this may be in your book. I don't know which page it is because I'm working from an older book. So I'll leave it to you to locate it in your newer text. Okay, so in this problem, the Greek mathematician Eratosthenes measured the circumference of the Earth from the following observations. Okay, he noticed that on a certain day the sun shone directly down a deep well in Cyrene. Okay, so the sun right here, here's the figure. And at Alexandria, or at the same time in Alexandria, 500 miles to the north, on the same meridian, okay, the rays of the sun shone in an angle of 7.2 degrees of the zenith. Okay, so whatever. So use this information to figure out the radius and circumference of the Earth. All right, so evidently we have, okay, so fortunately the author drew an illustration so we don't have to slog through all the complex terminology in the problem, but we can use the illustration to answer the question. So basically we have this angle. I think it's 7.2 degrees. Yeah, it's kind of washed out, but I'll illustrate it again. Yeah, so we have, here's the initial side of the angle, and the 7.2 degrees is this measure. Okay, so here's 7.2 degrees. All right, and then we have, so 7.2 degrees is this angle right there. And then we have this arc length is 500 miles. Okay, so we assume that the rays of the sun are parallel to the Earth. Okay. So what that means is that the angle, so that means that basically these two, okay, yeah, let me show you how it works here. So if I were to extend this line out like this, and then I were to extend this line out like right here. All right, so so if we make the assumption that the rays of the sun are parallel to the Earth like so, then we can just extend these two lines. So we've got this case right here. Okay, so these two lines that I'm accentuating in red are parallel. Now it turns out from geometry that if you have a line that cuts through two parallel lines like this black line is called a transversal from geometry. Okay. It's called a transversal. And there's a theorem called alternate interior angles. So from geometry, it was proven that the measure of this angle right here that I just accentuated has to be the same as the measure of this angle. So these two angles formed by a transversal slicing through two parallel lines has the same measure. Okay, so that's a carryover from geometry. So both of these angles that are demarcated here have the same measures. Okay, so we have then that the radius of the Earth, we want to find the radius of the Earth, and we'll call that r. So radius of Earth equals to r. So, and then using the formulas, we know that r is equal to s over theta. Okay? And so s in this case is 500. That's the arc length. And theta is equal to 7.2 degrees. Okay? Now we have to convert 7.2 degrees into radians because in order to make the calculation. So don't forget that when you have degree measure, you have to convert degree measure into radians to calculate distance. And we know pi radians is equal to 180 degrees. So we have this multiplying factor. And so when you do the calculations, turns out that the radius of the Earth back then was 3,000, and it was 3,000. Back then was approximated, not back then. Radius of the Earth hasn't changed, but anyway, what was thought to be the radius back then was 3,980 miles. Okay. All right. So I guess the tricky part here is zenith. The rays of the sun shown at an angle of 7.2 degrees to the zenith. So you might want to research what that term means, zenith, but yeah, I guess that would be the horizon or something like that. So, but that's how you would analyze the problem. And so now the next question is, what is the circumference of the Earth? So we know circumference of a circle is just 2 pi r, which is equal to 2 times pi times 3980. And that turns out to be approximately 25,000 miles. Okay, all right. Okay, so an application. Let me check to see if the book has a definition for zenith. I don't think they do. So I'll leave it to you to look that up. Yeah, there's no definition. But what zenith means in geometry. Maybe I should look that up. encyclopedia oftentimes gives accurate information. So, yeah, so here we go. The zenith is an imaginary point directly above a particular location on the imaginary celestial sphere. Above means in the vertical position opposite to the apparent gravitational force. So, okay, so zenith is the height of something. So maybe he was so maybe this was the point, the 7.2 degrees was the point at which the shadow disappeared. So, you know, if the rays are coming in, oops. Okay, so we can, let's see here. Can I copy this? So let's go back to our problems. And let's see here. Okay, so what zenith is, I know what it is now. Okay, so here's the guy standing on the surface of the Earth. And then you've got the rays of the sun coming at him in this direction. Okay, and so what happens is if a ray of the sun hits the guy, then it casts a shadow, and it's dark in this piece. So right here along this arc length, it'll be dark. Okay, but at the point at which you see light, so that's the point at which it hits the top of his head, and then there's no shadow cast. Okay, so the shadow ceases right here. And so you can take this to be this angular measure where the shadow stops to be the zenith. So I guess that's one way of looking at it. And the nadir, don't worry about what that is. So the zenith and the nadir. I guess it's the nadir would be this angle, perhaps, in the zenith. Okay, so just a little bit of what the 7.2 degrees means. I thought we should clarify that. All right. Interesting. Sometimes it's always a good idea to go back and check what these terminologies mean so that we have an accurate understanding of what's going on in the problem. So let's work another problem. Let's see, in this case, where does this one come from? Let me check. Okay, so yeah. Let me paste one into the whiteboard. So 1 second while I grab the problem. So let me select this piece right here. Okay, so for this problem, I'll write it down. Here's the illustration for it. And 3 circles with radii 1, 2, and 3 feet are externally tangent to one another. Okay. Find the area of the sector of the circle of radius 1 that is cut off by the line. Yeah, that's cut off by the line segments, that is. Joining the center of the circle. To the centers of the other two circles. Okay, and here's the illustration. So the blue circle, radius 3, centered at A. The red circle, radius 1, centered at C. And then the green circle, radius 2, centered at B. And then, so what we do is we take the center of circle C, and we join its center to the center of circle A and the center of circle B. Okay, and so we want to find the area of this orange or perhaps red shaded sector of circle 1. So you can see the illustration. So, so this is kind of an interesting problem. So what we have then, in order to calculate the area, we know that the area of a sector, we can start off with that. So the area of a sector is equal to 1/2 r squared theta. And in this particular case, r is equal to 1. Okay, so all we need to do is find the measure of angle theta. So we need theta, and once we get the measure of angle theta in radians, then we'll have the area of the sector. All right, so here's how we can deal with it. So we know that AC, what is the length of AC? The length of AC is equal to 3 plus 1, which is equal to 4. And we know this because the three circles are tangent to each other. Okay, so where the radius of A leaves off, the radius of C picks up. Okay, so the radius of A leaves off, the radius of C picks up. So there's no gap between the two radii, and that's true for the other other radii too. So where this radius leaves off, then this radius for circle B picks up. Okay, so there's no gap. All right, so AC is 3 plus 1, which is equal to 4. BC, the length of line BC, is equal to 1 plus 2, which is equal to 3. Okay, and AB, the length of AB, is equal to 3 plus 2, which is 5. So why did I do this? Well, first of all, it's the only quantities that we have, so we couldn't do any other types of calculations up until this point. But if you notice, whenever you have a 3, 4, 5 triangle, okay, a 3, 4, 5 triangle from geometry is a right triangle. Okay, and instead of writing out the word triangle all the time, why don't I just use this little symbol to mean triangle? Okay, so instead of writing the word, I'll write the symbol. So these lengths, the lengths of these three line segments, we can infer that it's a right triangle. So so that means that the length of the hypotenuse will be, how do we know that? So because it's a right triangle, if it is a right triangle, it has to satisfy the Pythagorean theorem, and it does. So because you recall the Pythagorean theorem, AB squared is equal to AC squared plus BC squared. Okay, and so we have AB squared is 25 is equal to AC squared, which is 16, plus BC squared, which is 9. So check. So it's a right triangle, satisfies the Pythagorean theorem. So that means the angle opposite the longest side in a right triangle. In other words, remember, the angle opposite the longest side in a right triangle is 90 degrees. And the longest side in a right triangle is often called the hypotenuse. Okay, so in this case, AB is the hypotenuse. So that means that the measure of angle theta is 90 degrees because it's the angle opposite the hypotenuse. So theta is equal to 90 degrees, which is pi halves radians. Okay, and we need the radian measure so that we can go back and calculate our area right here. Okay, so area then is equal to 1/2 r squared theta, which is equal to, say, pi fourth. Now, the measurements were given in feet, so this would be pi fourth feet squared instead of, yeah, pi fourth feet squared. Okay, so, all right, so let's do another word problem for section 3.1. The last word problem I'll do for this section. And I'll paste it in. So let me, bear with me while I paste it in. And this will be a problem essentially from mechanical engineering. Okay, so here we have the sprockets. Okay, so the sprockets, you have two sprockets in this bicycle assembly. The sprockets are these things right here shown in, here's a sprocket right here, this little round thing with the serrated edges on the circle, and then here's the larger sprocket right here with the serrated edges. And of course that's how you fit the chain. The chain right here connects the two sprockets. Okay, and so the pedal sprocket has a radius of 4 inches. So here's your pedal sprocket. Automobile engines have sprockets in them too. So the pedal sprocket has a radius of 4 inches, and the wheel sprocket right here has a radius of 2 inches. And the radius of the wheel, okay, so it's a 13-inch wheel. So we have 13 inches here. And I'll use this symbol, tick, tick, for the shorthand notation for inches. So we have 2 inches here, sprocket 2, sprocket 4 inches. Okay, and the cyclist pedals at 40 revolutions per minute. Okay, so that means RPM is omega. So omega is equal to 40 RPM. Okay, and we define omega. Remember, we defined that as your change in angle with respect to time. Okay, so RPM, not RMP, sorry. RPM, revolutions per minute. Okay, so that means in 1 minute, this wheel will spin 40 times. Okay, so so we have so the first question is part A, find the angular speed of the wheel sprocket. Okay, so we want to find the angular speed of the smaller sprocket. This is the wheel sprocket. So let me see, did I get that right? Oh, actually, I didn't get that right. I'm sorry, I had that wrong. I told you wrong. Sorry, that's not right. The we have the linear speed. Is that the linear speed? Yes, I'm sorry. Linear speed is in 40 revolutions per minute. So linear speed, how did I miss that? Linear speed is equal to 40 revolutions per minute. That means if I'm a point right here, okay, in 1 minute, I'm going to make 40 revolutions. So right here. So I make 40 turns in 1 minute, and that's the linear speed, not the angular speed. That's your change in position. How silly of me to do that. And so that would be distance traversed per time. Sorry. Okay. Now we want angular speed, so we need to convert linear speed to angular speed. So let me write that down. So for part A, convert linear speed to angular speed. Okay? All right, so here's how we do that. We use the definitions from the previous slide. So we have angular speed now, which is omega, and the formula is that will be linear speed divided by the radius of the sprocket. Okay. Okay, so that's the formula we'll use for this. Let me see if there's a reference. Okay, so that brings up the formula, the relationship between linear speed and angular speed. Okay, so I don't think I mentioned that. Let's see. Yeah. There's a formula. I need to take a checkpoint right here and give you a formula. We have, if you're converting between angular speed omega and linear speed v, okay, then the angular speed is proportional to the linear speed, and the constant of proportionality is the radius of the circle. All right, so in other words, the angular speed of the wheel sprocket, if I'm on the wheel sprocket, that is, okay, not here. I'm not here, but I'm here. Okay, so let me erase that. So if I'm on the, if I'm at the radius of the wheel sprocket, let's see, then we know that the wheel sprocket has to be turning at 40 revolutions per minute as well. Okay, and so the conversion is I take my linear velocity and multiply it by the radius, and I get angular speed. Right, so that's a formula, relationship between the two. All right, so we'll define that. That's the definition we have to work with. I forgot to give it to you in the other slides. Okay, so I'm glad I'm working through this example. All right, so the linear speed then is S over T, and what? Where were we given? 40 revolutions per minute. So we have to convert 40 revolutions per minute into radians per minute. Yeah, radians per minute. So that's one of the tasks that needs to be done. So let me write that down for you. Convert RPM, revolutions per minute, to radians per minute. Okay? Well, it turns out that 1 revolution of the wheel sprocket is equal to 2 pi radians. Okay, so there's your conversion. 1 revolution equals 2 pi radians for the sprocket. All right, so that means that our linear speed, so v would equal to 40 revolutions per minute times 2 pi radians per revolution. Okay, and let's see what else. Is that right? Let me see here. 40 revolutions per minute. There's a technical point here I'm not seeing. One second. Let me pull a reference here. The linear speed of the pedal. Four inches. Okay, so the pedal. Okay, so that would be. Oh, I see. So the linear speed. Okay, so there's another technical point that's not intuitively obvious here. The angular speed is not. Okay, I need to tell you which linear speed. It's not the formula I forgot to include here. Let's go back to our formula for omega. It's the linear speed of the pedal, because the pedal action is what's driving the linear speed. So linear speed of the pedal. Sorry, that's what I was confused about. I was hunting for an R value to convert the revolutions per minute into a linear speed. So the revolutions per minute, so the cycle is pedaling at 40 revolutions per minute, and so this 40 revolutions per minute is determined by the linear speed of the pedal. So in this case, it would be 4 inches, because that would be the linear speed of the pedal. Yeah, because so it would be. What was the formula for V? Let me check the formula for V. V is equal to. Where did I have that? V is equal to S over T. So S is basically right here, R theta. So S is equal to R. Here's your R value. And then here is your S over, this would be your theta over T right here. Okay. So in calculating V, we need a radius of some entity, and so the governing entity would be the pedal sprocket. Okay. Tricky question. So, all right. So we have 320 R, 320 pi would be your linear speed, and then the radius of the wheel sprocket is what, 2? Okay. Okay, so yeah, so then omega is, so omega would be 320 pi divided by the radius of the wheel sprocket, which is 2, and so that would be 160 radians per minute. So this is the trick in determining what V is. Okay, so V is determined by the pedal sprocket radius. The pedal sprocket radius determines your linear velocity. And this quantity right here is theta over t. Okay. All right. Okay, so that's the answer to part A, the angular speed of the wheel sprocket, determined by the essentially the angular speed of the pedal sprocket. Okay, so now the B part is find the speed of the bicycle. Assume that the wheel turns at the same rate as, let's see, assume that the wheel turns at the same rate as the wheel sprocket. Okay, so so all we have to do then is find the linear speed of the wheel sprocket. Okay, so we know then that the linear speed of the wheel sprocket, which is the linear speed of the bicycle, would equal to the angular speed of the wheel sprocket times the radius of the wheel sprocket. Okay, and so that would equal to 160 radians per minute times the radius of the wheel. Okay, because the angular speed of the wheel sprocket is the same as the angular speed of the wheel, as stated in the problem, and so the radius of the wheel is 13 inches. Okay, and so whenever you multiply inches by radians, the radians go away. All right, so this would equal to 2080 pi feet per minute, and if we were to convert that to miles per hour, that would be 74.26 miles per hour. Okay, would be the velocity of the bicycle. Yes, so sorry about the omission here. Omega, the angular speed of the wheel sprocket, is determined by the linear speed of the pedal sprocket. So that's the trick with mechanics here. That's why it's a mechanics problem. Okay. All right. So I think that's clear now. So that's what I'll consider section 3.1. So I will end this video and start another video for section 3.2 of the text. Right. So